Yeah, so I'm going to talk a bit about how you can generate all the data you need for a lot of AI development. Unity, just quickly, it's a gaming engine. It's the most popular gaming engine in the world. Over 2 billion players playing a Unity game or game developed on Unity every month. And wouldn't it be nice if we could turn this into something that could help us in AI? And games in AI is nothing new. I'm going to show you some epic moments in AI that were driven by gaming, starting with Claude Shannon and his chess algorithm. Go and Google it if you haven't done yet. There's a very nice PDF of that paper from 1949, 1950. It's amazing reading. Chinook in '89. Interesting. An example of an opening database, heuristic mid-game, and then a brute force at the end. Deep Blue, when I was at IBM, a chess program again, Watson, and then AlphaGo. Yeah. So some epic moments in AI development driven by gaming. Yeah. More recently, we have seen a lot of pixel-based examples, DeepMind, OpenAI, Atari, Doom, Quake, Minecraft from Microsoft, StarCraft with DeepMind and Blizzard collaboration, and Dota 2. So our biggest AI user of Unity is DeepMind. Here's a quote from Demis. About the excitement of using video games for advancing AI. Yeah? So what is it actually with video games that link them to AI? What is it that makes it useful? Yeah? And it's really kind of 4 dimensions. Number one, it's visual. It's this ability to use perception, to use sensory input. It's physical. You have physics in games. It's the cognitive aspect, the problem-solving aspect, and it's the social aspect, the multiplayer, yeah? So when you look at a real-time 3D engine, like Unity, as a spatial environment, it has a graphical rendering system, a multisensory system that I need to explain is the cameras. You can put cameras everywhere. The cameras can be RGB, so that normal cameras can also be depth. It can be a lot of different things. It can be sensor, collision, touch. There's a physics engine. And you have like a biodome for AI when you have a gaming engine, yeah. So let's talk a bit about simulation. I'm going to focus for autonomous systems only. It's really about sensing, understanding, and interacting. The perception element. I talked about sensors already. For supervised learning, we can use it for object labeling, semantic segmentation, domain randomization. We can generate all the data you need, all the visual data you need to train your convolutional net. Yeah? For behavior, it's reinforcement learning, deep reinforcement learning. I'm going to talk more about that tomorrow. But it's about observation, action, reward. And it's driving this. And there's a little detail here, which is not just reinforcement learning, but it's also imitation learning. You know about VR and all that stuff, augmented reality. The cool thing there is that you can actually have humans interact with these games to teach a system to do things. So you can sort of jumpstart it through imitation learning. Let's talk about perception first. We can generate data in these systems. In this case, here's an example of domain randomization. Notice that the textures are changing on the furniture. So what you can do here is that you can sort of train a system to recognize a chair no matter what kind of texture is covering the chair. There's changing of the lights. We can turn on and off the lights. So you can basically generate a lot of variations of your training data. Yeah? We can also get perfect label data. You don't have to have people labeling your data. You basically have the system labeling the data. It's 100% true ground truth. Yeah. In this case here, you see data generated for an autonomous vehicle training system. You see depth, you see segmentation. Here you see an example of LiDAR data. So the whole point here is to just generate all this data in a computer rather than driving a vehicle around and potentially hitting people. Yeah? Here's another example of generating different kinds of data, in this case, different kind of weather and light conditions, and basically generating this at scale. Yeah. So if you have one instance generating this, you can have thousands of instances generating this data in parallel. Yeah. Behavior. You want to train these autonomous systems to have really complex behavior that cannot really be coded by hand. Yeah? So to do that, we need things like reinforcement learning, which is about observing, taking action, reaping the rewards or the penalties, and over time, being really good at doing something. Yeah. I'm going to show you just a little example to make it more real. This is a pixel-based example. We basically want the chicken to cross the road. We're starting from a clean slate. As pixel observation, 4 actions, left, right, forward, backwards, and then you negative reward if you get hit by a car, or positive if you pick up a gift package. Yeah? So I'm going to show you just a little simulation example here. Initially, the chicken is just moving around randomly, has no clue how to do this, but very quickly will actually learn 2 things. Number 1, pick up a package, and number 2, get killed by being hit by a car. Yeah? But very quickly, through what I would call not trial and error, but trial and succeed, it learns to pick up gift packages and avoid cars to a certain extent. It's not good at it yet. But after 6 hours of training, now watch. Yeah. It becomes superhuman. Yeah. So it's very simple. It starts from scratch, and it gets really good at it. It actually gets superhuman entirely through simulation. Yeah? So we want to do the same for robots. Some good friends of mine tried it this way, with real robots. Yeah? Do the same thing as with the chicken. Yeah? Teach these robots or have them learn how to manipulate objects. Yeah? The problem here is that it just takes too long time. Yeah? So we need synthetic data. A game engine generates between 30 to 60 frames per second. It can go higher. We'll talk a bit about that. If you think about ImageNet with 20 million labeled images, I could generate those on a single server at 30 frames per second in 7 days. Yeah. More importantly, I could actually dynamically generate it, but we can get back to that. 1 year of your life at 30 frames per second is about 1 billion frames. Autonomous systems often operate at 10 hertz. Yeah? So we have to think about time when we talk about these frames in a different context here. So Planck time, yeah, sort of the time is not continuous, time is discrete, and Planck time is sort of the smallest unit. But what you have to think when you do simulation is that your smallest unit can be 60 frames per second, be 30. It can also be by event. So it's really a matter of the problem you're dealing with. Yeah? So here's an OpenAI example. They used Unity. They generated 30 billion synthetic images to train the robotic hand to do this. Yeah? So 30 billion is about 300 years of non-stop video simulation. Yeah? In the next example, solving Rubik's Cube, one-handedly, it's 10 trillion simulated frames. Yeah? So that's 10,000 years of video. So I'm only going to show you a small clip here of those 10,000 years. So let's talk scale. Actually, when we do these simulations, yeah, we can increase the frame rate. I don't have to run at 30 frames per second. That's just what the human eye likes. Yeah? I can run faster. I can also downscale resolution a bit, so maybe I run 4,000 or 5,000 frames per second, yeah? So that's, I don't have to stick to wall clock. Yeah? I can also run parallel. I can deploy 10,000 servers, I can deploy 100,000 servers, just a click and a credit card on GCP or AWS, yeah? So I can speed it up above wall clock time, I can do parallelism. I can also cheat a little, yeah, compared to nature, because I only have a single machine learning model I train, yeah? So sort of the idea of individual and species sort of goes away, because if I train for 10,000 years, or what's equivalent to 10,000 years of wall clock time, my individuals never die. Yeah? It's a single brain I keep training on. Yeah? I can also do checkpointing. Yeah? It allows me to step back in time and say, well, that part of my evolution didn't work well, so we're going to go back and redo it. Yeah? Nature can't do that either. Yeah? And then, as I said, I don't have to have all the fill frames in there. Fill frames are the things that goes on in between the important points. Yeah. So with that, I may run at 1 hertz, which means that when I generate 1 billion frames at 1 hertz, I cover many, many more years. Yeah. So when you actually look at simulation at real scale here, it gets very interesting, because you are sort of getting out there where you can do some tricks that are competing with what nature can do. Yeah. Have some publications that you can go and check out. Picture, yeah. And we also have more information. ML agents, that's our deep reinforcement learning framework for Unity. It's open source, it's on GitHub. Go and take a look at it. You can, we have a lot of users of that, thousands and thousands of users. And then also we have the Unity simulation, more information there about how to run Unity hitlessly in the cloud at large scale. And that's all I had for you. I have a talk tomorrow where we'll go more in depth on the deep reinforcement learning part. Happy to connect, and thank you for your time.